Hey guys, a very good day to you all. In this video, first of all, we will see what is catalyst and what is catalysis. Then we will understand the most important topic, that is the general characteristics of catalyst, which helps you to exactly understand what is catalyst and how does it work. Then we will see the classification of catalysis, and in the end we will understand a very short topic, that is nothing but inhibitors. So guys, make sure you all watch this video till the end so that you all get complete information regarding catalysis. Example of thermal decomposition of potassium chlorate. Now here what happens is that KClO3 is going to get decomposed into 2KCl plus 3O2. But guys, the problem over here is that this reaction takes place very slowly. So in order to make this reaction happen faster, what we do is that let's hit this reaction. And even after hitting this reaction, what we observe is that still this decomposition of KClO3 takes place very slowly. Now what we do is that we add MnO2, that is manganese oxide. Now as soon as we add manganese oxide, what we observe is that KClO3 decomposes rapidly. So guys, can I say that MnO2 increases the rate of the reaction? Now what is the meaning of rate of the reaction? Rate of the reaction tells us how quickly the reactants get converted into products. Now here guys, can I say as soon as you add MnO2, our reactant, that is nothing but KClO3, gets quickly converted into products. So guys, can I say since it gets quickly converted into products, which means that its rate has increased. And who has increased the rate? It is obviously MnO2 has increased the rate of the reaction. So here MnO2, manganese oxide, is your catalyst. And guys, this process of increasing the rate of reaction with the help of the catalyst is known as catalysis. So guys, I hope that by now you are at least clear with what is the job of the catalyst. The job of the catalyst is to increase the rate of the reaction. Clear with this? As simple as that. Now let us understand the 7 general characteristics of catalyst, and after understanding these 7 general characteristics, you will be clear with the concept of catalyst. Okay, so first characteristic is that catalyst takes part in reaction. Let's see how. We are going to understand this with the help of an example over here. Now here there is a reaction, SO2 plus O2 gives you SO3. In short, SO2 is getting converted into SO3. Now here we are going to consider NO2 as the catalyst. Clear with this? Now this reaction might seem a single step reaction for you all, but guys, this reaction occurs in 2 steps. In the first step, what happens is that this 2SO2 reacts with our catalyst, this NO2, which is our catalyst, and it gives us 2SO3 plus 2NO. Now guys, you might be thinking that we have now got our product. Am I right? We have got our product, so the reaction will stop over here. You are wrong. The reaction will not stop over here. And in the second step, what is going to happen is that this 2NO gets reacted with this O2, and it gives us 2NO2. Now, why there is a second step involved? when we have already got the product in the first step. The reason behind this is that we must get catalyst as it is. Now what is the meaning of this? See, we have added a catalyst over here, and by the end of the reaction we must get catalyst as it is. So as you can see over here, the catalyst got consumed and it got converted into products by reacting with SO2, but by the end of the second step we have got our catalyst back as it is. So guys, can I say that the catalyst is regenerated? Okay, now here obviously this is our catalyst, and this product that we get is called as the intermediate. Okay, this anode that we get is called as a intermediate, and obviously this 2SO3 is nothing but our product. Okay, this is our main product that we require. Now guys, obviously when you are going to add both this reaction, what you are going to get? You are going to get 2SO2 plus O2 giving you 2SO3. Now let us understand the points that are important in this example. The first point is that catalyst takes part in the reaction. As you can see over here, the catalyst has got consumed over here in the first step, and in the second step it has got regenerated. Okay, so in the second step we get our catalyst back. So guys, can I say, in the first step the catalyst gets consumed, and in the second step we get our catalyst back as it is. So here if you observe, yes, the catalyst does take part in the reaction in the first step itself. Now moving on, second point, the catalyst is recovered unchanged at the end of the reaction. So as you can see over here, by the end of the second step we get our catalyst as it is. We have given 2NO2 and we have got back our 2NO2. The third point is that catalyst takes part in the reaction, but it is not consumed. Here this is an important point. Don't get confused over here. Yes, the catalyst takes part in the reaction. It does get consumed in the first step, but by the second step is over, the catalyst is regenerated, which means that we get back our consumed NO2, that is our catalyst. So guys, overall, can I say, the overall if you see, there is no loss of NO2, which means that overall if you see, NO2 is not being consumed. It was consumed in the first step, but in the second step we got it back. So if someone asks you what is the total amount of NO2 that is being consumed, the total amount of NO2 that is being consumed is obviously 0, because in the first step 2 moles of NO2 was consumed, and in the second step we got back those 2 moles of NO2. So if someone asks you total moles of NO2 consumed, then it is 0. This is a very important point. Now, a catalyst does not appear in the overall balanced equation for the reaction. So as you can see over here, when you add both this reaction, the catalyst is not going to appear in the overall reaction, and this overall reaction, guys, must be similar to your original equation. Okay, so why it does not appear in the overall reaction? Because here it gets cancelled out with the left hand side, and this NO2 gets cancelled on the right hand side. So, and one important thing that you must notice over here, that NO2 does not appear in the overall reaction because NO2 has not been consumed. Is there any change in the quantity of NO2? No, there is no change in the quantity of NO2. Therefore, NO2 will not appear in the final overall reaction. That is nothing but this reaction. And this is also your overall reaction only. Okay, I have just bifurcated and shown you all that how this overall reaction takes place. This overall reaction takes place in 2 steps. Clear? Now, Moving on with the second general characteristic. The second general characteristic tells us that in a reversible reaction, catalyst increases the rate of both forward reaction as well as the backward reaction. Let's understand this with the help of a general example. Let's say we have a reversible reaction where A plus B gives us C plus D, and C plus D reacts with each other to give back A plus B. Okay. Now, if someone asks you what is the forward reaction over here, so obviously your answer will be the forward reaction over here is nothing but A plus B giving us C plus D. Now guys, here the catalyst is going to increase the rate of the forward reaction. And not only that, if someone asks you what is the reverse reaction, the reverse reaction over here is nothing but these products, right hand side products, C plus D giving back A plus B. So the catalyst is not only going to increase the rate of the forward reaction, but it is also going to increase the rate of the reverse reaction. So guys, in a reversible reaction, the catalyst increases the rate of both forward reaction as well as the reverse reaction. Clear with this? Many of you have a confusion that catalyst increases the rate of only the forward reaction. No, it increases both. It increases the rate of the forward reaction as well as the reverse reaction. This is a very important point and a tricky point that might be asked to you all in the competitive examinations like CET. Okay. Now, due to this, what happens is that the position of the chemical equilibrium and the value of chemical equilibrium constant is not affected. This I have already explained you all in the chapter chemical equilibrium. If you all want to watch the complete chapter videos on chemical equilibrium, then the link of the playlist is given in the description box below, or you can simply click on this I button which is present on the right top corner of your screen. Now, moving on with the third general characteristic. The third general characteristic tells us that extremely small amount of catalyst causes considerable increase in the rate of reaction. Now, what is the meaning of this? See, if you want to increase the rate of the reaction, it is enough if you add extremely small amount of catalyst. There is no need for you to add a very large quantity of catalyst. No, even an extremely small amount of catalyst will increase the rate of the reaction. Let's understand this with the help of the example over here. Okay, so one molecule of enzyme catalyst. This enzyme catalyst is nothing but your catalyst. This one molecule of enzyme catalyst under certain conditions decomposes 5 million molecules of H2O2 in just 1 minute. So you can assume, so you can see from here how much small quantity of catalyst is required. Just one molecule of catalyst can decompose 5 million molecules of H2O2, and that too in just 1 minute. Okay, so there is no need for you to add a large quantity of catalyst. Moving on with the fourth general characteristic. It tells us that a catalyst does not affect the energies of the reactants, nor it is going to affect the energies of the products, which means that it is not going to give energy to the reactant, nor it is going to take away energy from the reactant, and the same applies to the products as well. Moving on with the fifth general characteristic. A catalyst is poisoned by certain substances. Now, what is the meaning of this? There are certain substances that are present in the reaction which makes the catalyst inactive. Because of those substances, the catalyst becomes inactive, which means that catalyst cannot have its effect of increasing the rate of the reaction. Let's understand this also with the help of an example. Okay, before that, such substances which inhibit the catalytic activity are called as catalytic poisons. Okay, those substances in the reaction which make the catalyst inactive are called as your catalytic poisons. Clear with this? You'll understand this better with the help of an example over here. Okay, now in the conversion of SO2 to SO3, what happens is that platinum is used as a catalyst. And guys, even if there is a presence of trace amount of arsenic compound, then this arsenic compound will completely destroy the catalytic activity of platinum, which means that even if you add catalyst and if there's a presence of arsenic compound, okay, so if you add a platinum as a catalyst and if there's a presence of arsenic compound, then there won't be any effect of catalyst, because this arsenic compound is going to form platinum arsenide at the surface, and because of this there will be no use of platinum. Platinum will not be able to work as a catalyst, and it will also not be able to increase the rate of the reaction. And this is happening only because of arsenic compound that is being present over there. So this arsenic compound, which inhibits the catalytic activity of platinum, is called as your catalytic poison. Clear with this? This was a very easy point, not nothing difficult with this. The sixth one tells us that the catalyst increases the rate of the reaction which is already in progress. Okay, see, in most of the cases what happens is that a reaction is started, but that reaction is taking place very slowly. Therefore, we add a catalyst to it so that the reaction takes place faster. But in certain cases, what happens is that the catalyst is found to initiate the reaction, which means that when you add a catalyst, then only the reaction will start. Let's understand this with the help of an example again. Let's consider a mixture of H2 and O2. So we are having a mixture of H2 and O2. So this mixture remains unchanged for years. It is not going to react with anything. It is going to remain unchanged for years at 25 degrees Celsius. But as soon as you add your catalyst, that is nothing but a platinum wire, what happens is that now this mixture is going to start reacting, and it is going to start react so rapidly that the mixture is going to get exploded. So there are certain reactions who require catalyst even to start the reaction. Okay, but in most of the cases the reaction starts by the reactants itself, and we only require catalyst in order to increase the speed. There are very rare cases like the mixture of H2O2, H2 and O2, which requires a catalyst to start the reaction itself. Okay, I hope you are clear with this. Now guys, let us understand the seventh and the most important general characteristic. Okay, now first of all we will understand the graph for an uncatalyzed reaction, which means that in the reaction you have not added catalyst. Now on the y-axis we are going to have energy E, and on the x-axis we are going to have path followed by reaction. Now let's say that here are our reactants. I mean to say that reactants are originally going to have this much amount of energy. See, in reactants are initially going to have this much amount of energy, as on the y-axis we are having energy. Am I right? Now let's name this energy to be ER. That is nothing but the energy that reactants already have. So guys, can I say that this is the amount of energy that reactants already have? Now let's say that here are our products. Okay, now obviously if here are our products, then the products are going to have this much amount of energy, and let's name this energy to be EP. I'm explaining a general case over here, guys. Now, what is this orange color graph that is drawn over here? This orange color graph represents the path followed by the reactants in order to get converted into products. Which means that if the reactants want to get converted into products, they need to follow this path. Now, if someone asks you, at which point do we have maximum energy? Then obviously your answer will be this. At this point, there is a maximum energy. And if the reactants want to get converted into products, then they must at least have this much amount of energy. So guys, can I say that reactants initially have this much amount of energy, and plus they require extra this much amount of energy. This energy that they require in order to follow the path and get converted into products is called as energy of activation, or it is called as activation energy. Clear with this now? So if I ask you all that how will the reactants get converted into products, the reactants will follow this path, and via this path they are going to get converted into products. Now let us consider a graph for catalyzed reaction. Now in catalyzed reaction, what happens is that according to the four general characteristic, the reactants will have same amount of energy. Even if you add a catalyst, the energy of the reactants is not going to change. So your graph is going to start obviously from here. Okay. Now initially when the reaction was uncatalyzed, you are required this much amount of activation energy, but when the reaction becomes catalyzed, you now require less amount of activation energy, and obviously the energy of the products is also going to remain the same. So here are our reactants, here are our products, and now the activation energy required, the extra energy that the reactants require, is nothing but this much. So guys, can you all see over here that as compared to the uncatalyzed reaction, the path followed by the catalyzed reaction requires less amount of activation energy. Now if someone tells you that in a catalyzed reaction the activation energy is decreased, then that person is wrong. Here the activation energy is not decreased, instead the path followed is different. The catalyst forces the reactants to follow a different path in order to reach to the products. This is going to remain as it is. Nothing is going to happen to this activation energy. This is for uncatalyzed reaction. And for catalyzed reaction, the energy of activation is not going to decrease. Instead, it is going to follow a different path which has less amount of activation energy. See, this orange color path is going to remain as it is. Okay, so this is going to remain as it is. Nothing is going to happen to this path. Instead, now instead of going in this orange path, the catalyst is going to force the reaction to go in this green path which has less activation energy, and this is a major reason why the reactants get quickly converted into products. As if you observe over here, the path, the orange color path is more and it will obviously require greater time, and the green color path is less and it will require less time. So guys, I hope that you have understood what is a catalyst and you have got a fair idea about its general characteristics as well. Now guys, let us understand the classification of catalysis. I hope you all remember what is catalysis. Catalysis is a process in which we increase the rate of the reaction with the help of catalyst. Clear with this? Now, the catalysis is classified into two types. The first one is homogeneous catalysis and the second one is heterogeneous catalysis. So first of all, we will see what is homogeneous catalysis. So the basic definition of homogeneous catalysis is that when the reactants and catalyst are in same phase, it is said to be homogeneous catalysis. Let's understand this with the help of an example. Okay, so let us consider an example of oxidation of SO2. So this is the reaction in front of us, and as you can see over here, NO is acting as a catalyst. Now guys, NO is present in the gaseous state. Okay, it is present in the gaseous phase, whereas the reactants SO2 and O2, both of them are also present in the gaseous phase. So as you can see over here, the reactants as well as the catalyst, all of them are present in the same phase. Therefore, this reaction is called as homogeneous catalysis. Let us consider another example, last example, hydrolysis of ester. So when ester reacts with water, we use H plus ion as the catalyst. Now here if you observe, H plus ion is present in the aqueous form. Now let me tell you all that aqueous form also comes under liquid phase. Okay, aqueous means what? Presence of water, and water is obviously liquid. So aqueous form is also a liquid phase only. So as you can see over here, H plus is present in the aqueous form, this ester is present in the aqueous form, as well as the water is present in the liquid form. So guys, can I say that all the reactants as well as the catalyst are present in the same phase, that is nothing but liquid phase. So this reaction is nothing but homogeneous catalysis. Now let us move on to heterogeneous catalysis. So the definition of heterogeneous catalysis, you might have already guessed. It says that when the reactants and catalysts are in different phase, it is said to be heterogeneous catalysis. Now basically what happens is that generally the catalyst is solid state, it is present in the solid phase, and the reactants are either present in a gaseous phase or a liquid phase. So this is the general case that we observe. Now you need to keep one thing in mind, as the catalyst is present in solid phase and the reactants might be present in the liquid phase, the catalyst does not dissolve in the reacting system. Okay, the catalyst is not going to get dissolved in the reactants when you add it to the reactants. Okay, although the reactants are present in the liquid phase and the catalyst is present in the solid state, then too the catalyst is not going to dissolve. And the most important point over here is that the reaction is going to happen on the surface of the catalyst. Okay, so when the catalyst is solid, the reaction happens on the surface of the catalyst. I'm telling you general case. Okay, generally the catalyst is solid, and it is said that the reaction, and it is a fact, not said, instead it is a fact that reaction occurs on the surface of the catalyst. Now moving on, let's understand one example of heterogeneous catalysis also. So here we are going to consider the Haber process for synthesis of NH3. So this is the reaction in front of us, and you can see over here Fe is present in the solid state, and Fe is going to act as a catalyst over here. Okay, so this Fe is going to act as a catalyst, and these are the reactants. Okay, as you can see over here that both the reactants are present in the gaseous state and the catalyst is present in the solid state. So if someone asks you whether all the reactors and catalysts are present in the same phase, then your answer would obviously be no. All of them are present in a different phase, and hence this is an example of a heterogeneous catalysis. Now guys, we know one thing, that here Fe is the catalyst, but what is Al2O3 and K2O doing over here? So this Al2O3 and K2O are nothing but promoters. What is the meaning of promoters? See, when you add Fe to the reactants, the job of the Fe is to increase the rate of the reaction. But Fe is not able to increase the rate of the reaction significantly. So what happens is that we add Al2O3 and K2O, which helps the Fe to increase the rate of the reaction rapidly. Okay, now here Al2O3 and K2O are not catalysts. They are called as promoters because they are helping the catalyst. Okay, they are the helpers of the catalyst. So therefore they are called as the promoters. Okay. Now we need to cover a very short topic. We don't have to go into deep. The short topic, that is nothing but inhibitors. Okay. Now inhibitors is exactly the opposite of catalyst. Let's see its definition. The substances which decrease the rate of the reaction are called as inhibitors. And as we all know that catalyst increases the rate of the reaction, whereas the inhibitors decrease the rate of the reaction. Okay, so those substances which decrease the rate of the reaction are called as inhibitors. Let us consider another example over here. So here we are going to consider an example of dissociation of H2O2. So this is the dissociation of H2O2 that takes place, and the reaction is inhibited by addition of dilute acid or glycerol, which means that if you add a dilute acid or glycerol, then the rate of the reaction is going to decrease. So as can I say here, dilute acid and glycerol are nothing but your inhibitors. Clear with this? So guys, if you like this video, then please do not forget to subscribe to our channel so that whenever I upload a new video, you will be notified about the same and you won't miss anything. Okay, so make sure you subscribe to the channel and go check out my channel where I already uploaded physics and chemistry videos. They might be helpful for you all. And guys, thank you for watching this video.